Hi guys, this is a video specifically aimed at the last section of Unit 4 where we're looking at acceleration of a project, and I'm going to go through the steps of when calculating the acceleration. So first thing first is the contractor has certain reasons why he would want to accelerate, and basically he just wants to make more money and get a better cash flow by getting off the site quicker. So he would like to lessen his liquidity damages. Okay, then the client might have other reasons, which is he might want to open a store quicker, get a benefit of winter sales or whatever his reasons might be. So the concept that we're going to look at is simple. We're going to look at normal time, and we're going to look at normal cost in contrast to crash time and crash cost. Okay, so firstly we're just going to define these concepts. Is your cost slope is the critical path compressed as densely as possible. Okay, that's your cost slope. And then basically you can calculate your cost slope by having your increase in cost over your reduction in time, or you can have your crash cost less your normal time, which gives you your increased cost, or you can have normal time less crash time to give you your reduction in time. Okay, so basically if the project had a normal project time of or cost of £18,000 and as of £10,000, and if you accelerate it, you have 18,000, which is the cost. So your cost slope is then 8,000 divided by the difference in time that you made up. So your normal time is 8 days. 12 days, and then your accelerated time is your 8 days to give you 4 days, and simply you divide your difference or in cost over your difference of days to get your cost slope. Okay, fairly easy, standard. All of this is within your textbooks. Let me just get that page. Okay, it starts on page 186. Okay, so just explaining it a little bit better is you've got your normal time. Normal cost is you consider a network arrow for the activity of electrical services. For instance, your electrical services would have taken 12 days under normal circumstances, and or here it's just repeated. So that's your normal time. Crash time is by increasing the resources it would cost £18,000. Direct costs are increased thus. Okay, so your cost slope is basically your increase in cost over your reduction in time, or your normal cost and your normal time over, or your crash time less your normal cost over your normal time less your crash time, which gives you 18,000 minus 10, 12 minus 8 gives you cost slope of £2,000 or rands if you want to. Okay, so that's basically just a repetition of what we did in the first slide. Okay, so then we look at our direct costs. You've got our labor, e.g. bonuses. More labor is needed. If you accelerate it, your plant, you need to increase your plant. Material, more waste is produced. Subcontractors, direct and indirect factors for them, overheads and more admin, etc. Okay, so these are items that contribute to your costs. So your indirect costs is your normal P's and G's, for instance, project supervision, site hutting and accommodation, site office, telephones, heating, etc., buckies, transport, and so forth. Okay, then other definitions is your total project cost. It's the direct and indirect costs combined. optimum project durations is where the most beneficial least cost situation occurs, taking into account both direct and indirect costs. Okay, so we're going to look at your total cost and your project duration by means of a example. Okay, so just before we go into the example, basically we've got our total costs and our direct costs here. So, and then we've got our indirect costs. So basically you've got your indirect costs and your direct costs. Them, if you add that item and that item, you get that item on your total cost. Same with here, you can see what the difference is. Your indirect cost has a constant slope. That's like your P's and G's, your daily or your monthly costs. Your direct cost is your more plant, like we highlighted earlier, which escalates if you reduce the time needed. Okay, so that is basically the concept. So we're going to look at that now, and then try and plot this on a graph. Okay, go. Okay, so that's just the explanation of where it goes to, and then this is what we're going to aim to calculate is our optimum time. Okay, so getting into our example. So if we look at our two scenarios, figure 9.40 shows a construction sequence involving activity A to I in arrow diagram format. The tubular data indicate the normal times, normal costs, crash times, crash costs, and the indirect costs of the project, which amounts to £2,000 per week. Okay, so this is that £2,000 per week. So on page 189, you can start reading. That's basically what I'm referring to. So, and then on page 119, you will see this diagram. Okay. So in figure 9.41, the analyzed diagram based on the normal time situation, which gives an overall project duration of 28 weeks. Okay, so basically what they went to calculate is they just plotted the normal times to see what the actual normal time of this project is, because they you can't just add all of your days together, because they have different sequences. Like A takes 6, so they just added 6 here. B has a duration of 8. Sorry guys, this is not freehand. And then E has a duration of 6, and so forth. And then they calculate your critical path. I think on the next page we will be able to see that much better. But please have a look on this table and this diagram at your normal costs. This is information that's provided. Is total cost, okay, excluding the 2,000 per week, and then your crash time for these items is given here, and then your crash cost next to that. Okay, so to increase or to decrease item A to 4 days, it will cost you 20,000 pounds extra to do the work. Same with B, it will cost you to reduce it with 4 weeks, it will cost you £48 extra for reducing the time. Okay, so okay, the point that I wanted to make with this is just you can't just add all of this together, okay, because you're not going to get to the right answer. Okay, so just looking at this table, figure 9.41, the analyzed arrow diagram based on a normal time situation, which gives an overall project duration of 28 weeks. The total project cost based on normal time has been calculated at £254,000. Basically, it is your 28 weeks times 2,000, and that's added to your 98 direct costs, which gives you a final or total cost of 254,000. Okay, very simple to do. Is what they did is they just put in the time durations, and then they had a look at what the longest path is to see what the duration of the actual project is. So a simple way of doing that is starting from the back. I'm going to mark that in green, is and going backwards, so and looking for the longest path. Okay, so first item is D, that is on the critical path. That's 6 days. Then from here we can see that F is our next longest item, which is D, or given at 10 days. Then working from there, it's 6, and then from there on it's A, which is our other day. So it's 6 plus 6 is 12, plus 10 is 22, plus 6 is 28 days, which I calculated there. Okay, so this is basic stuff that you did in PQM last year and also doing in project management this year. So please have a look at that. Then just go, okay, here's the critical path that I just drew in. Okay, cool. Okay, so now you've established what the critical path is, and now you need to rate your items in order according to your cost slope. So now you put in your items in a table like this, and you have your normal time listed here, your crash time, your saving in time, and then you've got your normal costs, your crash cost, increase in cost, and then your cost slope here, and then you rank your items from there downward. So what they've done is they've put the critical path here, the items, and then they rank their critical path items accordingly. So A, E, F, and D are basically listed there, and then they rank them according to the cost slope. Okay, so D is your least D has the least impact on your, or has the lowest cost slope, with A having the second lowest, and then E the third lowest, and then F the fourth. Okay, so basically it doesn't necessarily work like this. I don't know why they ranked it like this particularly, but if you go to your basically they just worked from according to your diagram 9.41, they just drew in the critical path. So this is the critical path that they just drew in going on here. Okay, so these items do not apply because they're not on the critical path. Okay, so once you've done that and you've calculated which one has or the ranking accordingly, and then you also added or calculated the amount of time you save for each item, then you go to the next step. Okay, please guys, and this is also explained very well in your textbook, so please read through that. So scenario 1 is a reduction of 5 weeks in the project duration in order to complete the project by week 23. The effect on the direct and indirect costs will be considered in order to achieve this reduction. So you're giving the scenario that you need to reduce your time duration with 5 weeks. Okay, so what happens is, okay, so we've got that. Now you can establish, okay, what items do I need to reduce this this project with 5 weeks? So we can see immediately A, E, and F will apply, and we're saving 2 weeks, 2 weeks, okay, and then we're saving 4, but we only need one of these to get to our required 5 weeks. Okay, so keep that in the back of your mind, and I think on the next table it actually explains it very well. Okay, so figure 9.45, the summation of the direct and indirect costs is displayed, and a point of graph where the cost suddenly increases in the position to the optimum time at least cost situation. This occurs at the end of week 24. Okay, so let's first look at okay, let's look at table 9.2. Sorry for that, I just want to get that correct. Okay, here we go. Okay, so your scenario is what I basically sketched is we're going to look at items D, A, and E. Normal times is 6 weeks. Our crash time is 4 weeks and 5 weeks. But the reduction in time that we need is 2 weeks, 2 weeks, 1 week, like I highlighted in the previous one. So the cost slope is 3,000, 4,000, and 9,000. Okay, so for the number of weeks that we're reducing is 2 times 3,000 is 6,000, and 2 times 4 gives us 8,000, and 1 times 9,000 gives us 9,000. So reduction in overall time, we've decreased our project with 5 weeks, and it had an additional cost of 23,000 pounds. Okay, so just doing that calculation, you've got your direct cost is thus 98,000 plus 23 to give you a new indirect cost, or direct cost, sorry, and then your indirect cost is now, instead of 28, it's now 23 times 2,000, which is now 46,000, and then it is those two together. So now we've got a cost of 296, which is actually a bit lower than our initial, or slightly higher than our initial 254,000 pounds. So there was an acceleration cost of 13,000 pounds. Okay, so this is a question where I might ask, calculate what the cost implication would be to reduce your project duration by 5 weeks. Okay, so then you will use these tables 9.2 and 9.3. Okay, going to scenario 2. Now we're going to look at the optimum time reduction. So now we're going to look at the effect of the project cost for each week's reduction in time in order to assess the least cost situation. So the change in the direct and indirect costs due to each week reduction in the project time is indicated in 9.44. The relationship is presented in graphical form in 9.45. Okay, now that's what I read earlier. So the relationship between the indirect and direct cost for each week of the project from weeks 28 to 18 can be observed in figure 9.45, which basically shows that the summation of the direct and indirect cost is displayed, and the point on the graph where the cost suddenly increases is the position of the optimum time and least cost situation. This occurs at the end of week 24. At week 25, the change in cost per week alters from 2,000 to 7,000 per week. Okay, then the project costs have been analyzed back to week 18 in order to see the overall cost implication. So basically we're going to look at, okay, so basically this is just a summation of the previous scenario 1. So we looked at D, E, and A. So okay, we've already dealt with that. Skipping to scenario 2, to find the least costly amount. So this is what I've read now in 2 slides ago. the time at which the aggregate cost escalates substantially. Okay, so that's just the summation of it. Okay. So what we've got is we've got our normal direct costs and our indirect costs, which has our total cost at 254,000. Okay, so now let's say we reduce our project with 27 or with 1 week. It will add 3,000 pounds of direct costs to our project, and it will remove 2,000 indirect cost from our project. So aggregate cost is added of 1,000 pounds. So our project, to decrease our project with 1 week, is it will add 1,000 pounds. Okay, so then we do the same, reducing it with 1 week, we add 3,000 and we subtract 2,000, so aggregate of 1,000 is added, and we are at 256,000. Okay, that's for activity D. Okay, then we do look at activity A, which is, if we reduce it with 1 week, here we add 4,000 pounds and we subtract 2,000 for our indirect costs, and then we've got an aggregate of 2 and 250,000. Okay, so you can see it's fairly straightforward. D, A, E, and F. Okay, cool. So you can see the ranking. I just wanted to make sure that this is right. So the rankings in the critical path items are still according to table 9.42. So table 9.42, you still need to use to actually rank your items according to that, the ones that has the least impact. Okay, and then we look at item 20, or still with item A, we reduce it with another week, and we still add an aggregate of 2. Then we do the same, and here we can see here's a substantial increase, jumps to 7,000, and here it goes to 8,000. Okay, and then it wasn't taken any further than that. Okay, so that is now figure 9.45. So all that we do now is we plot this on a graph. So our direct or indirect cost is very easy. We've got our normal cost is 55,000, and we reduce it with to was it 56? Sorry, 56,000. We reduce it with 2,000 each week that we reduce our project duration with. Okay, very straightforward. And then our increase of items, our direct costs, is as per the previous table. You just plotted. So initial one is 196, reducing it with 1 week, we get to 201,000, 204,000, 206, and so forth. And then we can see here it starts to jump from 212,000 to 221,000. Okay, and then going up, just adding this one to that one, we can see that we've got a big the slight jump here, and then here's that 7,000 jump that we highlighted in the previous table, which means that our optimum line of time least cost is at week 24. Okay, so the main thing about this exercise is to go through this example, work through it systematically, and just do the same whenever you asked a question in the exam or in the test, to just refer to this and just apply this rationale. So let me just show, this is where the major jump is. and that's the optimum timeline. So yeah, so please have a look at this, and if you do have any questions, please do not hesitate to contact me. Thank you guys. Bye.